Welcome you all on my YouTube channel, Mathematics for All. So today's discussion topic is bilinear transformation. So this is very useful topic that we study in the complex analysis and in the conformal mapping. So before studying this bilinear transformation, you can study the linear transformation and the conformal mapping. This is Brajesh Kumar Jha from Department of Mathematics. I welcome you all on my YouTube channel, Mathematics for All. If you are new, you can subscribe our channel for more updated videos, and you can like, subscribe and share with your friends. So now let us see what is bilinear transformation. And basically we are going to discuss three type of questions usually asked in examination related to bilinear transformation. So this video is very useful for BSc, BTech and MSc students. So the transformation that we know W is equals to AZ plus B, this is called the linear transformation. As you can see, it has a linear behavior. So if A is equals to A0 e to the power I theta, if you put, then the linear transformation can be seen as a combination of these translation, rotation and stretching. So to study about the translation, rotation and stretching, you can follow the previous videos. Here we will discuss about only the bilinear transformation. Now the transformation which is in the form of W is equals to AZ plus B CZ plus D, provided AD minus BC is not equals to 0. This is called the bilinear transformation. It is also known as the fractional transformation or Mobius transformation. So do not be confused with the terms. These are all the same: bilinear transformation, uh, fractional, and the Mobius transformation. So here this you can see it has a two part, AZ plus B and CZ plus D. So by having some values, you can define this all in the form of translation, rotation and stretching. Also, if you put here A is equals to 0, so it will be B upon CZ plus D, or if you can put D is equals to 0, so your transformation will be in the form of W is equals to 1 upon Z with some constant, let's say K. So it is a one kind of inversion. So inversion can be shown in the bilinear transformation only. And these three, translation, rotation and stretching, can be defined by using the linear transformation as well as the bilinear transformation. A, B, C and D are complex numbers. Now this bilinear transformation, as I stated earlier, can be defined in the form of translation, rotation, stretching and inversion. Bilinear transformation have the different property. It has first property that the circle in the Z plane are mapped into the circles in the W plane. So this is the beauty of this bilinear transformation. Circle means it may have the infinite radius, so the straight line can be defined as the circumference of the circle having the infinite radius. The expression AD minus BC is called the determinant of bilinear transformation, that you must remember. Some property that we can see in the bilinear transformation, the product of two bilinear transformation is also again it is a bilinear transformation. Inverse of a bilinear transformation is again the bilinear transformation. So W is equals to suppose I write here AZ plus B upon CZ plus D, or if you could write W is equals to A1 W, for difference I have taken A1 plus B1 upon C1 W plus D1. So it is also the same what it is a bilinear transformation, but the thing is it is the inverse of the transformation. Now we talk about the word that is a critical point. So let fz be a non-constant analytic function in a domain D and f dash z is not equal to 0 for some z0 in D. Then this z0 is called the critical point of the transformation. And you must see here fz is the non-constant analytic function. So we will see in the examples as well. Otherwise it is called what? Ordinary points. If we consider the bilinear transformation w is equals to az plus b upon cz plus d, let's say it is dz, we get the inverse mapping or transformation z is equals to t inverse w, that is b minus wd wc minus a. So that you can frame here w is equals to az plus b upon cz plus d. So by multiplying here you can get czw plus dw is equals to az plus b. So z you can take this side and dw you can take this side, and by taking z common you get here what? cw minus a is equals to b minus dw. So in that case, by having this, z is equals to b minus wd upon c w or wc minus a, that you can get. So this is the inverse transformation of w is equals to fz or tz. Now after critical point we study the fixed point. It is also known as invariant point of the transformation. So the points which coincide with their transformation are called the invariant or fixed point of the transformation. So w is equals to fz is the bilinear transformation, let's say. So if you put w is equals to z, so z is equals to fz if you put. So whatever we get the value of z, that will be defined in the form of fixed point or invariant point. So the fixed point of the transformation w is equals to az plus b upon cz plus d, that is given as z is equals to az plus b upon cz plus d, and by rearranging it is a form of quadratic equation that we get. Quadratic equation in z. So by solving you can get this here, a minus d plus minus a square root of m upon 2c, and by defining the m, b square minus 4ac of the ordinary quadratic equation that we have taken here. So the number of fixed point is 1 or 2 according to m is 0 or m is not equals to 0, that we get. If m is equals to 0, so you will have only 1 a minus d upon 2c as a fixed point. If m is not equals to 0, so you will have the 2 fixed point. So when c is not equals to 0 and if m is not equals to 0, then one has the fixed point, 2 fixed points that can be given by z is equals to this a minus d plus minus square root of m upon 2c. If m is 0, then one has only the one fixed point as stated earlier. If c is equals to 0 and d is not equals to 0, so it will have the fixed point that z is equals to b upon d minus a that we get. So by putting w is equals to z, you will get this result. If a minus d is not equals to 0, then one fixed point that will be infinity and other finite fixed point that you will get here. If a minus d is equals to 0, then the transformation has only one fixed point, that is infinity. So these are results that you can analyze when you are going to get the fixed point. Now the next very important term that we see in the bilinear transformation, that is the cross ratio. So if z1, z2, z3, z4 are the distinct point, and then the ratio that we define z4 minus z1, z2 minus z3, z2 minus z1, z4 minus z3 is known as what? Cross ratio of these 4 points, and this can be defined in this way. So the equation of the circle passing through the 3 given point that can be written as in this form: z minus z1, z2 minus z3 upon z2 minus z1, z minus z3, and complex conjugate in the same manner, same fashion you can put here. and you will get this result. So this is the cross ratio. This is very important topic that we study in the bilinear transformation. Z is any complex variable lying on the circle. Now we see the questions related to bilinear transformation. Find the bilinear transformation or mapping. Z is equals to 210 to W is equals to 10I respectively. So in such questions, we require to find the bilinear transformation W is equals to Fz. So how we approach this? We approach using the cross ratio. So cross ratio that we have written here in the form of Z, here in the form of W. You can see it has the same pattern. So one pattern if you remember, second pattern you can automatically you will get. Now we put all the values here. So Z1 is what? Z1 is 2, Z2 is 1 and Z3 is 0. Same way W1 is 1, W2 is 0 and W3 is I. So by putting all the values of Z1, Z2, Z3 and W1, W2, W3, we get this initial information. Now by solving this, so this will be multiplied by this one, and here it will be multiplied by here the cross multiplication that you can perform. So by performing the cross multiplication, we get the value W is equals to this one. So it is defined in the form of what? W is equals to Fz. So this is the bilinear transformation that we get the result. Now come to the next. Here what we can see in the points, it has the infinity as well in both Z and W. So Z is equals to infinity, that is Z1 is infinity, Z2 is I and Z3 is 0. Here W1 is 0, W2 is I and W3 is infinity that we get. So for the solution, what we see, let Z map to W. Again we apply the cross ratio. So by applying this cross ratio and putting this value of this one. So here since Z1 is infinity, so we have kept it is Z1. And in the W3 is infinity, so that we have kept the W3 as it is. Now what we do, we take Z1 common and the W3 common in the factor. So by taking this common, so Z1 will be cancelled here and W3 will be cancelled here by taking the common. As Z1 and W3 is infinity, so the whole this fraction is going to be what? 0. Same way I upon W3 is going to be 0 and W upon W3 is going to be 0. As W3 and Z1 is infinity, it is given. After that, what we left here, it is minus 1, it is I, it is again minus 1 and it is Z. So we will simplify the values. So by simplifying, we get the W is equals to Fz. And Fz is what? Minus 1 upon Z. So this is the required answer. So here I have considered both type of questions when the points are given the finite values, and other way it has the infinite values. Now we can analyze the from the property of bilinear transformation that Z1, Z2, Z3 and Z4 are the concyclic and it is purely real if it happens. Second is if the set of all bilinear transformation forms a non-abelian group under the product of transformation. The bilinear transformation maps family of circles and straight line to family of circle and straight line that we analyze in the bilinear transformation. Now W is equals to 1 upon Z transform circles and lines into circle and lines. So these are the remarks that we can see. The bilinear transformation maps inverse point with respect to a circle to the inverse point of transformed circle, circle to circle that can be transformed. So every bilinear transformation is the result of an even number of the inversion. And the last one is what? Every bilinear transformation maps the family of circle, that is the argument of Z minus Z1 upon Z minus Z2, that equals to R, where R is not equals to 0. Throw the fixed point that we have Z1 and Z2 onto a similar family in the W plane, though the two fixed points W1 and W2, which are the transformation of the point Z1 and Z2 under this bilinear transformation. The last one, the property that we can see, and it is also stated in the form of theorem. So let fz be a function analytic at z0 such that fz0 is 0, and if f dash z has a 0 of order k minus 1 at z0, then the mapping w is equal to fz magnify the angle at the vertex z0 by the factor k. Now we see again some questions related to bilinear transformation. Find the image of the circle mod z minus 3 is equals to 3 under the Mobius transformation w is equals to z upon z plus 1. So w is equals to z upon z plus 1, that gives here w by taking the cross multiplication, that is wz plus w is equals to z, and what we get here by taking this z common, w minus 1 is equals to minus w, that we get. So z is equals to w upon 1 minus w, that is the inverse transformation we get here. Now we use this inverse transformation in the given circle. We have to find the image of this circle. So z minus 3 by 3 can be written as what? Mod of z minus 3 square is equals to 3 square, and z minus 3 mod of z minus 3 is equals to 3 square, that we know z bar is equals to mod of z square. By using this property we have applied. Now we put the value of z, that is w upon 1 minus w here. So what we get, z minus 3 is this one, and z bar minus 3, that we can get this one. So by putting this in equation 2, it will be what? 4w minus 3 upon 1 minus w, and 4w bar minus 3 upon 1 minus w bar. This is equals to 9, that we get. Now we simplify this all terms, and by simplifying, what we get here, 7w bar minus 3w plus w bar is equals to 0, and w is what? W is equals to u plus iv, that we know. So w bar will be what? U square plus v square, that is w bar will be u minus iv. So by multiplying, you will get u square plus v square, and w plus w bar, if you adding here, so you will get 2u here. So by simplifying this, what we get, u square plus b square minus 6 by 7u is equals to 0. Now as we know, this is the equation of a circle, so it will have the center, that is 3 by 7 0, that you must go through the calculation and verify this answer, and the radius will be what? It is 3 by 7 again. So the image of the circle mod z minus 3 is equals to 3 is a what? Circle with the center 370 and the radius 3 by 7 in the w plane. This is our result. So the circle mod of z minus 3 is equals to 3 is mapped in the form of this one. Now we come to the question number 4. Find the bilinear transformation which maps z is equals to 1, I minus 1 respectively onto w is equals to I 0 minus I. Also find image of mod z less than 1. So earlier it was mod of z minus 3, now it is mod z only. So again what we do, we have the cross ratio. By having the cross ratio, what we can get the bilinear transformation. So this discussion we have done earlier in the few examples. So directly I go to the bilinear transformation that we get. W is equals to 1 plus iz upon 1 minus iz. After that, what we see, first thing, this is the required bilinear transformation. Now we have to map this under this bilinear transformation. So this bilinear transformation, again it is rearranged, and inverse bilinear transformation that we get here in the 1. Now our in the domain it is given mod z less than 1. So by putting this, what we get, mod of z square is what, z bar, which is less than 1. So z is that you got here. Similarly, you can put z bar L as well. So by putting z and z bar, the equation can be defined in such a way. So in equation 2 that we have kept the value of this one. So by putting this, what we get, 0 less than or 2 times of w plus w bar is greater than 0, and w plus w bar is also greater than 0, and w plus w bar that we know it is a real part of w, that is u, because w is equals to u plus iv that we know. So in this case, mod z less than 1, that is mapped to the real part of w, that is u, which is greater than 0. In this way, we have obtained the bilinear transformation against the given point, and after finding the bilinear transformation, we have mapped the circle. Now let us see the question number 5. Here the question given that we have to find the fixed point and the normal form of the bilinear transformation. So we have already discussed about the what is fixed point. If you put w is equals to z, you will get the value of z, which will be known as the fixed point. So what we do here, we put w is equals to z here. So by solving this quadratic equation, what we get, z is equals to 0 and z is equals to 3 are two fixed point. Now to get this normal form, what we do here, this we can get w minus 0 upon w minus 3, and that you can put z minus 0 upon z minus 3. So by solving, what we get here, it is in the form of w is minus 0 upon w minus 3, that will equals to k times z minus 0 upon z minus 3. So here we have kept the value of w. So by solving, we get here. So once we go for the value of k is what, minus 1 by 2 or minus 1 by 2 e to the power I pi, that we can write. So in this way, we can understand that the given transformation is logarithmic that we get. Now we can see the question number 6, that find the fixed point and the normal form of the bilinear transformation. W is equals to z minus 1 upon z plus 1. The same fashion we will do here. We put here w is equals to z, and by putting the w is equals to z, what we do, we can solve this. So by solving, it will be z square plus z, and this z will be minus z plus 1 is equals to 0, and finally it is z square plus 1 is equals to 0. So z square plus 1, that we can write z plus I into z minus I is equals to 0. So z is equals to I and minus I, that we get as a fixed point. Now to get the normal form, what we do here, first we get for w minus I. So w minus I, by putting w is equals to that transformation that we have. So by putting, we get this result. Same way w plus I, that we get this result. So dividing these two, we get here w minus I upon w plus I. Z plus 1 will be cancelled, and this will be simplified form. Now by rearranging this, what we get, w minus I upon w plus I is equals to what, minus of I z minus 1 upon z plus 1. So this is the normal form. Here minus I that we get, that k is equals to minus I, so it can be written as e to the power minus I pi by 2, and mod of k is equals to 1, so that's why it is a form of elliptic form. So in this way, we can have the number of questions related to bilinear transformation. So basically, three type of questions that we have discussed: how to find a cross ratio and a bilinear transformation, and then the mapping of the different circle under the bilinear transformation, and the third one, how to find the fixed point and the normal form of the bilinear transformation. So hope so you have enjoyed this video. So thank you for watching this video. You can like and you can subscribe our channel for more updated videos, and you can share with your friends if you found it is useful. Once again, thank you for watching this video.